All right. Let's just get into it. Okay, so this section, I was like, when I had to do the homework, which was a couple of days ago, I did not really get this section. When a basis B is chosen for an n-dimensional vector space, the associated coordinate mapping onto Rn provides a coordinate system for V. Each x in V is identified uniquely by its B coordinate vector xb. Think of B as a name for x that lists the weights used to build x as a linear combination of the basis vectors in V. In some applications, a problem is described initially by using a basis B, but the problem's solution is aided by changing B to a new basis C. Each vector is assigned a new C coordinate vector. In this section, we'll study how x in C, how are you supposed to say it? The C coordinate vector x and the B coordinate vector x are related for each x in V. Okay, let me just get this crap out of my pockets. To visualize the problem, consider two coordinate systems in figure 1. X equal to 3b1 plus b2 and 6c1 plus 4c2. So they're the same point in space, right? It's just what we're using as our basis. Consider two bases, b1 and b2, or b and c, for a vector space such that b1 is equal to 4c1, b1 is equal to 4c1 plus c2, and b2 is equal to this. Now suppose that x is, so then 3, 1 is, the b coordinate vector of x. Now to find c, so do we solve for C1 in terms of B1 and B2? Okay, the solution is apply the coordinate mapping determined by C apply the coordinate mapping determined by C to x in 2. Since the coordinate mapping is a linear transformation, we can pull it out as a linear combination. We can write this vector equation as a matrix equation using the vectors in the linear combination as the columns of a matrix. See, this is where I get so confused. So what this means is how to construct B1 from the basis of C1, or from C in general. So then you get, 4, 1, and minus 6, 1. But I don't get why the matrix vector product gives us the Okay, I'm trying to. So earlier we had b times x, the b coordinate vector of x is equal to x. So take, okay, because this vector is how to construct x from the basis of b. That's why it's 3, 1. Now, so because what these are, b, I mean, 4, 1 is b. Okay, yeah. So 4, 1 is how to write b1 in terms of c's basis. Yeah. Okay. All right. I think I'm sinking in. So, okay, and then the general theorem of this two-dimensional example is let B and C be bases of V. Then there's a unique n by n matrix P such that you can multiply a vector x written in terms of basis B and convert it into a vector written in terms of basis C. The columns of P are the C coordinate vectors of the vectors in the basis B. Okay, it's called the change of coordinates matrix from B to C, and it converts B coordinates into C coordinates. The columns of P are linearly independent because they are coordinate vectors of the linearly independent set B. Since P is square, it must be invertible by the invertible matrix theorem. Left multiplying both sides of the equation by P inverse yields the change of coordinates matrix from C to B. So that takes a vector written in terms of C's basis and gives you back something written in terms of B's basis. Okay, change of basis in Rn. If B and E, where E is a standard basis, then B1 written in terms of the standard basis is just B1. In this case, P from B to E is the same as the change of coordinates matrix PB introduced in 4.4, which is just the, right. That's what's so weird. It's like, yeah. Okay, to remember how to construct the matrix, think of P from B to C times X in B as a linear combination of the columns. The matrix vector product is a C coordinate vector, so the columns should be C coordinate vectors too. Right, yeah, if you think about it as a linear combination and not just some like abstract matrix vector product, then it maybe makes a little bit more sense. Okay, all right, that's kind of making some sense. To change coordinates between two non-standard bases, we need theorem 15. Theorem shows that to solve the change of basis problem, we need the coordinate vectors of the old basis relative. We need the coordinate vectors of the old basis relative to the new basis. Okay. So we have B1, B2, C1, C2. Consider the bases given by B1 and B2 and C1 and C2. Find the change of coordinates matrix from B to C. Okay, so it involves the C coordinate vectors of B1 and B2. So basically, we're going to be solving. So if we make this matrix, C times X is equal to B1, and then C times X is equal to B2. Right. Okay, sure. They write it like this. So we're solving, yeah, this equation and this equation. To solve them at the same time, we can just make a big augmented matrix and row reduce. Okay, great. Okay, so this is the P from B to C. So now we can take any vector written in terms of B and convert it to something written in terms of C. So like to write this first basis element in terms of C1 and C2, you would take 6 times this, which would be 6 minus 24, and then you'd subtract, so wait, let me just do that. So you'd have 6 times 1 minus 4 plus or minus 5 times 3 minus 5. So this becomes 6 minus 24 plus minus 15 and 25, which is equal to minus 9 and 1. Cool. All right, nice. So yeah, so if you take this vector, this first column, B1 in terms of C, and you multiply it as a linear combination of C's basis elements, then you're going to get back B1. Yeah. Great. Yeah, I it was a detrimental thing to rush through this section for sure. Because I was just like trying to get it done, and I was just like rushing through it, but it's actually not that complicated. Okay, another example. All right, cool. So that's actually the whole section. That's really not that complicated. Wait, is my mic working? Test? All right, yeah. Okay, so, oh wait, there's some stuff at the end here. By part A in property 6, you can just take the inverse. Another description of the change of coordinates matrix from P from B to C is the oh yeah, okay, wait, this is new. Okay, use the change of coordinates PB and PC that convert B coordinates and C coordinates respectively into standard coordinates. Recall that for each x in Rn, we have PB times XB equals X and PC XC equals X. So X in terms of C is going to equal PC inverse times X. Okay, so we can do it as 2. So because we can get X from, yeah, okay, so you can, okay, so I'll write that down. That's pretty interesting. So since PB times XB equals X and PC times XC equals X, we also get X is equal to PC inverse times, oh wait, this is X in terms of C, and this is just going to be times X. Then X, to get XC, we can take XC is equal to PC inverse X is equal to PC inverse times PB times XB. All right. So that's pretty straightforward, actually. All right, on to the problems. I haven't gotten to break out my new whiteboard yet. Maybe I'll do that today. All right. So the practice problems. Let F and G be bases of V. Let P be a matrix whose columns are... So this is going to be the change... Okay, which of the following equations is satisfied by P for all V? Okay, because we have how to write the basis F in terms of G. Then we have, F1 written as G and F2 written in G. So then this is going to take... God, see, but this is where I don't know why it's just so confusing to me. So yeah, so this is going to take a F chord vec and give it as a G chord vec. Okay, all right. So yeah, so this is the change of coordinates matrix from F to G. So it's going to be 2 is correct. But this one's not going to be always true. Okay. So that's problem 1. 2, let B and C be as in example 1. Use the results to find the coordinates from C to B. Okay. We'll just do that with an inverse. So where's example 1? Okay, so we have 4 minus 6, 1 and 1. So we're just going to invert that matrix. So if A is equal to 4 minus 6, 1, 1, we just take inv of A. Is that right? We're going to get 1 over 10, what is it, 3 over 5, minus 1 over 10, 2 over 5. All right, let's check our answers. Nice. And then, since the columns of P are G coordinate vectors, a vector of the form Px must be a G coordinate vector. Okay, so I want to just like hammer out a bunch of problems just to drill it in, because this section is confusing for me. All right, let's just read through them all and then we'll do them. So B and C are bases, and then you have B in terms of C. So this is B1. So 6 minus 2 is B1, is the C coordinate vector of B1. Find the change of coordinates matrix. Find XC. Okay, so then this is going to be, so this X, if you write it in terms of these coefficients, is going to be, minus 3, 2, and that's going to be the B coordinate vector of X. So XC is going to be the matrix vector product of this coefficient matrix times this coefficient vector. Okay, so this is the same one. Okay, 3 is let U and W be bases for V. Let P be a matrix whose columns are U in terms of W, and which of the following equations is satisfied? So in this case, it's going to be this one. So you're going to take a vector in D, and it's going to rewrite that as a linear combination to satisfy, so if you gave, let's see, if let's go back to the original example. Right, so if you gave 1, 0, 1, 0 would be corresponding to this point, because because you're talking about stuff in B. But then what this is saying is that you actually have to take 4 steps, or what, you have to go 4C1 plus C2 in order to get to B1. And so when you multiply 1, 0, you're going to get yeah, so it's written in terms of now the bases of C. Or the C basis. Okay. So in this case, right, we're going to get, you're going to provide a vector written in terms of D, and it's going to switch that around so that it's written in terms of A. Because what these are is telling you how to write the basis of D in terms of A. So then, so the answer is going to be 1 here. All right, number 5 is let A and B be bases of a vector space V, and suppose that A1 equals 4B1 minus B2, and okay, so so if you take these coefficients again, you're going to get the B coordinate vector of A. So find the change of coordinates matrix from A to B. So wait, hold on. So in 5, I'm going to do these all more formally, but I need to think about it. So what we have is A1 B coordinate, then B coordinate of A2, and then A3B. Okay, and so what that gives us is a way to take a vector in A and give you a vector in terms of B. Okay, so 3 through 6 is all just reinforcing that idea, which is good. I mean, I like that. I think I'm gonna just do all those just because. All right, so 7 through 10, let B and C be bases for R2. In each exercise, find the change of coordinates matrix from B to C and from C to B. Okay, not so bad. So we'll probably do an RREF. We'll make the augmented, and then we'll do an RREF. Okay, so those are all pretty straightforward. Then here we have a couple of true falses. We'll do those. We always do the true falses. True falses are the best. In P2, find the change of coordinates matrix from one basis to another basis. Then find the B coordinate vector. Okay, so finding the B coordinate vector, we're gonna so let me remember. So what we're gonna do is we're gonna write this down in terms of the standard basis, which would just be the vector -1, 2, 0. And then what we're going to do is do a linear solve. So each one of these is a vector, and it's going to be the column. And in fact, it's the way to take like a vector in B and give you a vector in C. I feel like it's really helpful to, like, if you think about what like 1, 0, 0 does, because then you're gonna like see this first column is 1, minus 2, 1. Now if you give 1, 0, 0, then it's just going to be this first column, and that vector is written in terms of the standard basis. So that's kind of nice, right? A nice way to like help check your understanding. All right, in P2 find the change. Okay, so it's the same one. In 17 and 18 provide a proof. Given V and V, there exist scalars such that the linear combination of X and B equals V. Because A, apply the coordinate mapping determined by the basis C. Wait, I'm lost. What? We'll definitely do that one. So let me just write down what we have so far. So I am going to do 1 through 6 because they'll be easy. So this is 4.6. And we are finally going to get to eigenvectors today. We're going to be trying to do 5.1 and 5.2. All right, so we have 1 through 6. Then we'll do just like 7 and 9. Then we'll do 11 through 18 at least. Is there any ones we want to skip in there? Maybe we'll not do 16. We'll probably not do 16. Okay. Oh, and that's pretty much it. But let's read through the calculator ones. So B and C, where xk is the function cos to the k and y is the function cos kt. Exercise 54 in 4.5 showed that B and C are bases for the vector space Whoa, that's weird. Maybe we'll do that one. Explain why the columns of P inverse are the C coordinate vectors of x0 to x6. Then use the coordinate vectors to write trig identities expressed. Okay, that one's weird. Maybe we'll do that one. Recall from calculus that integrals such as they're really tedious to compute. The usual method is to apply integration by parts repeatedly and then use the half angle. Use the matrix P or P inverse from exercise 19 to transform and then dude, we gotta do 20 and 19. That's crazy. Okay, so 19 and 20 are for sure. 19 through 20. All right, what is 21? Find a basis for R3 such that P is the change of coordinates matrix. Oh yeah, this one was a homework one actually. Maybe we'll do this one. What is it asking? It's saying find a basis U for R3 such that P is the change of coordinates matrix from U to V. So if P is from U to V, then that means that we're going to have the bases U. The columns of P are going to be the U's written in terms of V. So it's going to be the V coordinate vectors of U. So what that means is that I believe that U is going to be the linear combination, like what I think that means is that U1 is going to equal, V1 minus 3V2 plus 4V3. We'll do 22. 22 seems good. 21 and 22. There's not that many problems in here, so we can just... I think that's it, right? Yeah. All right. So let us get into it. Let me just write them down. Okay, so we're doing 1 through 6, 7, 9, 11 through 22. We're probably going to skip some, but that is what is going on. Okay. Problem 1. Okay, so we have B, C bases of V. And then we have B1 is equal to 6C1 minus 2C2. And B2 is equal to 9C1 minus 4C2. So what that means is that B1 C is equal to 6 minus 2, and B2 in terms of C is equal to 9 minus 4. So then our matrix P C from B is equal to 6 minus 2, 9 minus 4. Okay, hopefully that makes sense. So this is part A. Part B is find XC for X equal to minus 3B1 plus 2B2. Okay, so what that means is that X in terms of, the B coordinate vector of X is equal to the vector minus 3, 2. Okay? So, so now that we have P from B to C, we can just take this and multiply P, C from B with minus 3, 2. And I'm just going to use a calculator to do that really quickly. So we have P is equal to 6, 9, minus 2, minus 4. And then we're going to multiply p times minus 3, 2. And that will give us 0 minus 2. Okay, great. So I'm just going to check in the back of the book for that. So this is section 4. I think we skipped section 4.5, right? No, we didn't. Okay, never mind. Where is section 4.6? Here's 4.6. Okay, so yeah, so 6, 9, and then 0 minus 2. Okay, great. So that's correct. We'll just do one more of these. Like, why not, right? Okay, so problem 2 is we have, it's the exact same setup. It's just B1 is equal to minus C1 plus 4C2. And B2 is equal to 9C1 minus 4C2. So we're going to get, so for part A, this is just going to be minus 1, 4, 9, minus 4. Okay, and then part B is going to be just the matrix multiplication of, this is P, this would be P times 5, 3. And we'll just leave it at that. That's enough of that. Okay, problem 3. So problem 3 is let U bases of V. Okay, let P look like this. U1 in terms of W and U2 in terms of W. Which is true. Okay, so what this is saying is that it's telling you, U1 is equal to, x1 w1 plus x2 w2, where these are like coefficients of the linear combination. So they're scalars and these are vectors. So then what you're given is that so what that means is that if I and same for U2 is equal to what do they call it, y1 w1 plus y2 w2. And so this matrix is going to be, x1, x2, y1, y2. So the idea is if you give like 1, 0, you're going to get, it's going to be the linear combination of these column vectors, right? So you're just going to get, this is equal to x1, x2, which means that because 1, 0 is written in terms of the bases of U1, and now we're rewriting it in terms of the bases of W. So this is going to be the equation, P, it's going to be P from U to W times U or let's just say X in terms of U is equal to X in terms of W. So let me see which one is correct. It's going to be, so the answer is 2. Let's just check my answer. 3 is 2. Good. Okay, so we're just going to do 5. We're not going to keep going with all this because it's like the same stuff. Or actually, this one's different. 4 was the exact same. Okay, so 5 is A equals, A1, A2, A3. And B also bases of V. Okay, and then you get A1 is equal to 4B1 minus B2. A2 is equal to minus B1 plus B2 plus B3. And finally, A3 is equal to B2 minus 2B3. Oh, this is just find the change of coordinates. Okay, so A is find P from A to B. Okay. Okay. So this is going to be, so A1 in terms of B is equal to 4 minus 1, 0. Then A2 is equal to minus 1, 1, 1. So anyways, P is equal to 4 minus 1, 0, minus 1, 1, 1, and 0, 1, minus 2. Okay, then part B is find x in terms of the basis B for x equal to 3a1 plus 4a2 plus a3. So you have to recognize is that x in terms of a is the vector 3, 4, 1. So now, since this matrix tells you how to convert a vector in A to a vector in relative to B, then you just take the matrix vector product again. So I'll write that out in my program. So just say P is equal to 4 minus 1, 0. Minus 1, 1, 1, 0, 1, minus 2. And then we can just do P times 3, 4, 1. Okay, is equal to, so P times X A is equal to 8, 2, 2. I'm just going to check if that's correct, but it's almost certainly correct. That was problem 5. Yep. All right, we got it right. All right, so we're going to skip 6. So what do we have done? We have, we're going to do 1 through 6, 7, 9, 11 through 22. All right, so let's do 7. Okay, so problem 7 is, all right, I'll just write it out. It's easier than switching back and forth. Okay, so in this we have B, C, bases of R2. Okay, so the problem is find P from B to C and P from C to B. Okay, so I'll just write out the matrices now. Okay, so what we're gonna do so if we were to do like B, C, and we row reduce it, we're gonna get I, and now which is this gonna be? This is gonna tell you so what this is solving is B times X is equal to C1. And what that means is that wait, let's call it wait, yeah. So I believe that this would be the mapping, so that when you solve this, this is going to be P from B to C. I want to check the answer, but I want to make sure I got this right logically. I don't want to just look at the answer. Right, because what this would be is X would be then X would be linear combination of the basis B columns to form C1. Okay, so this would give you, you know, that C1 is equal to like, you know, let's say A1 times B1 plus A2 B2 or something like that, where A1, A2, and R, these are scalars. And so then you get so then you get so what this means is that this would be that X would be so the vector A1, A2 would be X in terms of B, right? So then that checks out. Or would it be, it would be probably, you'd write C1 in terms of B. Yeah, you'd write C1 in terms of B. Okay. So, yeah, so my answer for 7 is that this is converting a basis B into basis C. But then to find P from C to B, you could either take the inverse or you could just row reduce C, B, and row reduce that into I, P from C to B. So I'm pretty sure that that's what you just need to do. But let's switch into a program to do the row reduction and solve it. So we have B is equal to, so I'm just going to do it as a matrix. So it's going to be B, or 7 minus 3, 5 minus 1. And then P, or C is equal to 1 minus 2, minus 5, 2. And then we can do H cat B, C. So this like stitches them together to make them augmented. And then we ref this. And actually, I like to convert them to rationals just in case there's some goofiness there. Okay, perfect. So then P from B to C would be equal to minus 2, 1, minus 5, 3. And what we can do is we can check, just to double check, is this means that we can write C1 as minus 2 times B1. So if we did, okay, so this is the P, we'll call this PBC. So from B to C. And if we did, or let's lowercase this, PBC. So this is going to be, so let's do just the third column. So if we multiply this by or well, we'll do this. We'll do C times, or wait. No. It's going to be B times this. So if we get B times this, then we should get the first column of this. Perfect. Nice. See how there was a 1 minus 5? And that's the first column of that. So this definitely is so PBC, this last 2 by 2 is definitely how you write. Wait a minute. Am I getting confused? This is how you write C1 in terms of B, right? This would be C1 in terms of B and C2 in terms of B. So wait, did I get it flipped? That's what I'm so confused about. Because what we're saying is that I feel like I did get it flipped around. I think that this might not be, I think this might be PCB. Wait, let's just go back to basics. Okay, so in problems like 1, you have B, so 6 minus 2 is B is the C coordinate vector of B1. So when you solve, okay, so like when we solve for Bx, when we solve for the basis matrix B times some x, and we solve for x equaling C1, then yeah, we're getting C1 in terms of B. So I'm almost positive now that this is actually PCB. Okay, so let me think about this. No. Okay, wait. Here's what I'm trying to figure. When we solve b backslash c, what this means is we're solving b backslash first column and then the second column. Okay. We should probably make those rational, but that's fine. And so this is a linear combination of the columns of B. So these weights are in terms of the basis B, which means that this is a B coordinate vector. Okay, so now I'm almost positive that this is P from C to B. I'm now ready to check because I feel like that is the actual answer. So if we go and we look at this example, we have C. Where is this thing? Okay, so we have C to B, and this goes from so what did I say? I had wait, I'm so confused. Okay, if you have C next to B and you row reduce it, then so if C is on the left, then you get so was I right? Yeah. So eventually I did get the right answer. That's good. All right. That was a good problem. Hey, what's up? Yeah. So what you have to remember is that when you do this row reduction, you're writing it in terms of the left-hand side because that's what the product means. That's what that means. Okay, so all right, so I'm gonna actually do. So wait, that was 7. I'm just gonna do number. Oh wait, we never actually found. We never actually found. Um, um, so if instead we do CB, then we should get PBC is equal to RFCB. Okay, so let's just check if these two are correct. So this was 7. So from B to C, from B to C is equal to -3, -5, 1, 2. From B to C. Good. All right, we did it. Thank God. That was brutal. Okay, for 9, we have -6. So B is -6, 2, -1, 0. And C is 2, 6, -1, -2. All right, let's just plug it in. All right, so we're going to get B is equal to -6, 2, -1, 0. And C is equal to 2, 6, -1, -2. And now if we do this, so if we hcat them together, what we're going to be solving is we're going to be solving for the matrix X such that B times X is equal to C. And so that's what B \C is. And so this will be equal to RFBC. 1, 4, 2, 9. And what that means is that X is going to be the B coordinate vectors of C. So X in this case, so X is going to be PB. This is going to be, since it's writing C in terms of B, it's going to be PB. Wait a minute. Hold on. I got to think about this. B times X is equal to C. So you're going to be writing, C1 in terms of B and C2 in terms of B. So this is going to be okay. So what does that give you? This gives you I prefer it like this. This is easier for me. So this is going to be writing C1 in terms of B. And then this is C2B. So so therefore the matrix of C1 B C2B, this is effectively it's like C1 is equal to like let's just say A1 times B1 plus A times B2. So this is C1. This is the B coordinate vector of C1. The B coordinate vector of C1. This is just how to write, C1 B. One sec. But why is this so confusing? I always. So if I have this matrix. Wait, this isn't right. What the hell? Yeah, so I'm pretty sure that this is PCB. Okay, so let me do the problem again. So for 9, is that what we have? We have 9 minus 6, 2. Okay, so what I'm saying is that PCB is equal to B backslash C. What the? And PBC is equal to C backslash B. So let's just check that that's true. Okay, so this is PCB. So for 9, PCB is 1249. Nice. All right, if we got that one, then the other one's definitely right. But let's just do this. Then 9 minus 2 minus 4, 1. Okay. Those are definitely really good problems, at least for me. They're so confusing. Okay, so if I were to write it out, so B backslash C is equal to P from C to B because it's equal to, like, so we have Bx equals C1, By equals C2. So okay, all right. You just got to write it down enough times and then it starts to sink in, I think. Okay, finally, true false. The columns of the change of coordinates matrix P from B to C are B coordinate vectors of C. P from C to B is okay, so P from C to B is how to write the basis C in terms of B. And it takes a C coordinate vector and returns a B coordinate vector. And therefore, the columns of P from B to C are the B coordinate vectors of C. Oh, wait, that's from B to C, not C to B. Oh my goodness, I'm so confused. So in this case, you're going to be writing B in terms of C. So this is false. So 11 is false. The columns are linearly independent. That's true. Or wait, is it always true? Yeah, if they're both bases of the same vector space, then that's got to be true. If C is the standard basis, then that is true. If V is equal to R2 and B and C are bases, then the row reduction produces a matrix. So right, so what are you going to be, so what does this turn into? This turns into, you're solving C backslash B, right? And C backslash B, is that that's the same as R ref of the H cat of CB, right? Let me just double check. So hold on. So we have B backslash C. So B back C. And then we have okay. And we have okay, so yes, these are equal. So what does that mean? That means that this solves for x, where B times x is equal to C. So if we did B times so x is how to write C in terms of B, right? Then in other words, x are the B coordinate vectors of C. So then x, otherwise, i.e., the B coord vex of C. Which means that you take a vector in B So yeah, so then we get like C1 is equal to 2 times B1 minus B2. Wait. Oh wait, did I do it wrong? Because wait. What is x? Wait, B times x equals C. So x, so this first column is a linear combination of the columns of B. So this should be 1, 4. I don't know where I got that fucking. There we go. Which means that these x takes right. X is the column vectors of C in as linear combinations of B's basis. Otherwise, no. So then, we're really going around in circles on this thing. So for this, for this one. This is solving C backslash B. This is solving for X. So it's going to be writing. So X is going to be writing B in terms of C. B terms of C. So I think that this is, so Cx equal to, solving Cx equal to B gives you the B to C matrix. So I think that this is false. Okay, so 14 false. Man, these are doozies. Okay, so we got them right. Okay, let's keep going. Problem, what did we say we were going to do next? Oh, we're just going till 22. All right, so we're just doing the rest of them. Okay. So problem 15. All right. Change of chord matrix from B equal to, I'll just write out the matrix. So this is to the standard thing. So this is 1 minus 2, 1, 3 minus 5, 4. And 0, 2, 3. Okay, so otherwise these columns would be like 1 minus 2t plus t squared. Okay, to the standard basis. So I think that this is, so I think B is P from B to C. Because if we multiply it by xb, like let's say that we want 1, 0, 0. Or rather, actually, let's say let x equal what am I trying to say? If this is 1, 0, 0, then x equals 1 minus 2, 1. So yeah, so if x equals 1 minus 2, 1, hold on, I'll be right back. Okay, yeah. So 15, you just write these coefficients as columns in a matrix. Okay, then find the B coordinate vector for, then find xb for x equal to -1, 2, 0. So then the way to do that is, we'll just do it in a calculator. So we have b is equal to 1, 3, 0, minus 2, minus 5, 2, and 1, 4, 3. And then we have x is equal to minus 1, 2, and then we can just do this. And then we should get xb is equal to 5 minus 2, 1. Let's just check the back of the book. So this was 15. So good. We got P, B to C right, and then we got this XB right. Nice. Okay. 16. This is the same thing as before. Let's just go to 17. Okay, provide a proof of theorem 15. Theorem 15 is change of basis is a crazy section for me. I wonder if other people also find this as trippy as I do. Okay. So problem 17 is, given v and v, there exist scalars x1 to xn such that the linear combination because... Wait, what? I guess I'm gonna say because b is a basis and therefore spans v. That's what I'm gonna say. For A, I'm gonna say it's because b is a basis that spans v. Apply the coordinate mapping determined by the basis c. So the coordinate mapping of c is from x to x relative to c. Okay, and B is because chord map is a linear transformation. The equation may be written as a matrix vector product by the definition of linear combination. I'm going to say, okay, C, I don't know. C, I'm going to say definition of linear combination. Definition of linear combination. I don't know. That seems wrong. But then D, I think, is invertible. Because the vector on the right-hand side of 8 is invertible. And by that, I just mean it spans it and stuff like that. So 17, B is a basis. Coordinate mapping is linear transformation. Okay, so I said product of linear or definition of linear combination, but also, matrix vec product, mat vec prod definition. And then the coordinate vector v relative to b. What is that? Because the vector on the right-hand side, oh, yeah, I totally got this. I don't know what, I wasn't even reading it. I was just like guessing. That's so lame. Because the vector on the right-hand side of 8 is, the b coordinate vec of v. Is that what it said? Yeah, b coord vec of v. Okay, yeah. All right, 18. Okay, so suppose Q is any matrix such that C chord of V is equal to Q times the B chord of V. So for 18, we have VC is equal to Q times VB for all V and V. Let little v equal to the B1. So wait, so Q must be this is interesting. Yeah, so set V equal to B1. Then 9 shows that B1C is the first column of Q. Yeah, that's true. Because if V is equal to B1, then VC must be B1C, which is the first column of Q. But I don't know. Yeah, let's just look at the answer. Wait, we don't have the answer. Yeah, whatever. Let's skip it. All right. Should we do? We definitely have to do 21, but let's look at 19. Okay, so 19. Let B equal to x0 to x6. C is y0 to y6. Where xk is the function cos t to the k, or cos to the k t. So is the first basis not just 1? I'm pretty sure the first basis is 1. So if we were to just make a, what's up, man? Nice to see you here. All right, so wait, hold on. So let's just get our basis x. So it's going to be map cos, or let's say at variables t, map cos t to the k, or let's just say n. Oh wait, we have to make an anonymous function. And then this is going to be 0 to 5. There we go. Okay, cool. So that's x. Now y is equal to map n to cos t times n, 0 to 5. Okay, there we go. So exercise 54 in section 4.5 showed that both b and c are bases for the same vector space H equal to the span of B. Interesting. So set P, so this is going to take a C coordinate vector and give it in terms of B. So ooh, that's crazy, man. So for 19, P is equal to the so this is going to be writing cos. Well, this is 0. So what is y for 0? It's just 1. Okay, so let's figure this out. So for the let's say for y1 in terms of b, we're gonna say cos t is equal to, okay, so they agree there. So let's do y2 then. So y2 in terms of the basis b, we get cos 2t is equal to some linear combination of these. So let me try this. So if we have, we're just going to try to make the equation. We have cos 2t is equal to, and this is going to be like, how do we do like a linear combination? So this is going to be the sum of k. Ooh, how do we do this though? So I want a linear combination. The eq is, yeah. Yeah, but because I mean, this is what I would do, but what is solve always though? Wait, what is the difference between that and solve? Gives the values of parameters that make the equation. Oh, that's interesting. Okay. Oh wow, I've never even seen that before. That's cool. This is really nice. I like this. So you have n equal 5, m equals 2. Okay, what is array though? I've never seen array. Generates a list of single. I think it's because this. Whoa, list plus, that's not right. Oh, that's so weird. Part, oh, because part ranges over 0. Oh yeah, okay, that's fine. I'm down with that. Okay, there you go. So a1 plus a2 cos t plus a3 cos squared. And this, we need it to be, yeah, there's 6. That's correct. So the highest power is 5. Okay, then we solve for this. Inverse functions are being used. I don't think that's what we wanted. Can we not just do solve in terms of coefs? Wait, I don't need to do this. We can just do this. Nah. It's not exactly what I wanted. Because Yeah, like, uh, no, but that's cheating, man. I don't know about that. That feels like cheating to me. Like, okay, how would I derive or write down by hand the way to write cos kt as linear combination of cos to kt? It's pretty cool. Jebby Jev. Whoa. What problem is this? 19. Can I look at the answer for 19? I'm just curious if that code does it. Let's just see if this is right. N equals 6. Or wait. That doesn't seem like the same thing, right? Oh, maybe it is. 1/2, 3/8. What's the last one? 10. 7. Oh, so they were right. We need to change this to 6. 5/16 times 32. Yeah, that's 10. Okay, so this is right. I didn't, not that I understand it, but so what is the Chebyshev polynomial? That's, I guess, what we need to know. These expressions define polynomials. Huh. Wow, that's crazy. Okay. That went way harder than I thought it was. Right, because it's way easier to take like coasts. Oh, that's so cool. Okay, so we can write this in terms of. Oh, that's actually so sick, man. That's really, really cool. So yeah, so we can take this, which is going to be, so it's going to be, okay, so it's going to be, let's see, we have one, um, so our basis is, so we have one, cos t, cos squared t, cos 3t. So we're going to have 0, 0, 5, right? Minus 6, 5, minus 12. Okay. So that is, so this vector is equal to x relative to the basis b, where b is the cos to the kt. So now our change of basis matrix is P inverse, right? Because P is the change of basis from Y or from C to B. So then P inverse is equal to the B to C. All right, so we just need to multiply this by xb, and we get x in terms of c, and then we can compute the integral really easily. So then we just need to, okay, so let's do this. This is cool, man. Okay, so wait, first off, we need to, okay, so let's just say that xb is equal to 0, oh wait, 0, 0, 5, minus 6, 5, 12, minus 12. So then Pn dot xb. Really? What's the shape? How do I get the size? How do I get the shape? Shape of an array? Tensor size Wolfram? Maybe I should have said shape. No dimensions? Oops. I always forget that thing. 7 by 7. And then 6. Okay, wait. So, but the highest power is, can I look at calls? Wait, but calls are just the coefficient list. But it's only supposed to be 6, right? Do I need another 0 at the front? 1 cos t cos squared. Oh yeah, I think I need another 0 because we have cos 3, but this is going to be so I think it's going to be like this. And then how do I just take the, if I have two lists, if I have two lists of the same length, how do I take the linear i.e. sum ai times bi? Oh, it's just dot. Yeah. Okay. So all right. So what do we need to do? We need to say, I'm just gonna say our basis is equal to, or yeah, basis is equal to, it's gonna be the table of cos t to the k for k 6, and then we just do xb dot basis, right? Then we get cos 5 minus 6. Okay, perfect. So this is exactly what we wanted. So now we just need to, now we can just do this, right? So this is, so if we were to, so basis 2, let's call it b2 is equal to, it's going to be table cos kt k 6, right? So then if we just say that this is going to be the xc coordinate, right? So then we're going to have b2 or xc dot b2. So presumably this is, then this is the integral that we need to take or something like that. Maybe we could just double check and just say, so this is xc, let's call it xcc. I don't know what that means, but if we just do integrate xcct, something does look wrong because I don't know if we should have a power there, right? Why would we have a power there? Maybe this simplify just did that. But if we integrate, let's call this xbb. If we integrate see, they're different. That's why I'm kind of sussy. But they might be the same, right? Ugh. Huh. So, okay, wait. But how do I check if two polynomials are equal? Oh, cool. All right, so I think we did it right. That's so sick, man. That's so freaking cool. That you can take like instead of having to do integration by parts like a million times, which that sounds awful. You can just you can just use oh, that's so cool, man. All right, that was fun. All right, let's do 21. 21 I really want to get right cuz I had such a big problem with it when I was doing the homework. Could you imagine pulling this trick out on a test? You like your teacher's being mean and gives you a crazy integral that you have to just do a bunch of integration by parts and you just pull out this thing, this change of basis. That is really weird. All right. 21. P is this and V is this. Find a basis for U. Find a basis U for R3 such that P is the change of coordinates from U to V. Okay, so P is something we're trying to find. So you're trying to find U. So what that means is that this is going so P is going to be gosh, why do I always get this confused? All right, I'll be back in a second. This is I just always forget which direction it goes. Okay. Okay. Wait. So Okay, so what was our I mean, this is like the last problem. So so we're trying to find basis that makes P the change of basis from U to V. Okay, all right. So the columns here um so the columns of P is a linear so what I'm saying is, so I think that U1 is going to be equal to like 1 times V1 minus 3V2 plus 4V3. So it's going to be the linear combination of this with the basis of V. So I think it's going to be V times P. So if we Hey, what's up, Hansi? No, yeah, I've just been okay, this section on change of basis, bro, is like, oh my goodness, it's so confusing, dude. I swear, change of basis is like the hardest section that we've gone through. Okay. All right, so we have P and V. So what I'm saying is that if we just take P's first column, okay, and we do V times that, then this should be U1. Because it's going to be equal to, so then what that means is that the U is going to be this. So that's what I'm saying. So I think that the columns of B to C represent the basis B written in terms of C. So then if you have a vector in B, the linear combination becomes the new linear combination that's equivalent in terms of C. Okay. Okay, so what I'm saying then is that the U is equal to minus 6, minus 6, minus 5, minus 5, minus 9, 0, 21, 32, 3. That's what I think it is. All right, part B, find a basis W for R3 such that P is the change of coordinates from V. So the change of coordinates, so for part B, the change of coordinates from V to W is going to be equivalent to the basis of V, so the VI, written in terms of W. Okay? So, so if this P, what does that mean? That one of these columns and VI in terms of W is, it's going to be like 1 minus 3, 4 written as a linear combination of W. Or it's not, it's going to be that you're writing, oh my gosh. Bro, this stuff is, it's too much, man. So what I think it is you're writing V in terms of W. You're writing V in terms of W. So I think what that, yeah, so what this means is that you're going to have like you're going to have like V1 is equal to W1 minus 3W2 plus 4W3. Okay, so the linear combination of this with W is equal to this. Because you're writing this in terms of a linear combination of the basis W. Okay, yeah. So that's right. So you're going to get V is equal to PW. So then I think what you need to do is you need to do in P times V, and that's going to be W. So I'm pretty sure that this is W. 21, 10, 11. Minus 13, minus 7, minus 7. And minus 3, 4, and 4. All right, let's just check if I'm right. That was I want to do that problem again. I feel like I need to do that problem like every day for the next week before it like really... This whole section, man. All right, so where are we? We're at 21. Six minus 5, 21. All right, cool. So we did it right. And then this one, I did not do right. Damn it. What the hell? I'm just curious if I did. That's the right one. But why is that the right one? If you have... Oh, wait, because... Hold on. It's WP, not PW. But why? Okay. Because... So... Yeah, so it's actually V times... But, okay. So what they're saying is if... Let's just do the whole problem again. So if P is P from U to V, what is U? And P from U to V is going to be writing the basis U in terms of V. Okay? Which means that this column represents a linear combination of V. So each column of P represents a linear combination of these basis vectors. All right. So that means that then we can do U is equal to, like V1 minus 3V2 plus V3, right? And so on. And that is V equivalent to V times P. It's not P times V, it's V times P. So is that what we had? I forget. We had V times P, yeah. So U is equal to this. Okay, so that one was correct. But then we failed on part B, where we have P is now V to W, which is going to be equal to the basis V written in terms of W. So then like V1 is going to be equal to W1 minus 3W2 plus 4W3. And that's going to be equal to W times P. Yeah, it's W times P. So you got to be really careful that you don't treat matrices as commutative multiplicatively, because that's not right. So now if you get V is equal to WP, then you multiply both sides on the right by P inverse. So then you get VP inverse is equal to W. Wait, is this the wrong one? Yeah, this is the wrong one. So you get V times in P. W is equal to that. Okay, cool. Wow, we're almost finally done with this section, but I imagine that I'm gonna need to come back to this. I mean, we spent 3 hours on this, and I still feel like I keep getting confused by the syntax and all sorts of stuff that's just like really confusing. Okay, 22. Let B, C, and D be bases. Write an equation that relates. Ooh. Yeah, so we need to reread that last note in the book, which is that let's say if you have a coordinate in xb and you want to take it to coordinate in xc, you can do P inverse C PB XB. Okay, so if we're going to try to write, so we want to try to write so what I okay, if we wanted to write P from B to C in terms of the other two, so B to C, it should be equal to this is going to be back, so it's going to be P from B to D. Okay, so it's and then the inverse C to wait. Okay, so what I'm saying is for this, we're gonna have PCB. So that means P from C to B is equal to inv PCD times PDBD times XB. Well, we don't really need this part. But that's what I'm saying. And then the other ones are just the same thing. That was a tough section, man. I shouldn't have included B. I just want A. All right, that one wasn't that hard, but 21, 19, and 20, these three were really good. Okay, cool. All right, so that is change of basis. That was a crazy section. Now, I think we're going to finally move on to eigenvectors and eigenvalues. Finally.